Good day. Okay, so today we're going to take a look at your compound microscope. Yes, your compound microscope. This will be our companion until the end of general histology laboratory. Okay, and so with that, let's take a look, of course. And so this one will magnify the organisms or materials that are not that cannot be seen by the naked eye. Okay, and so let's take a look at the parts of your microscope. Okay, and so with this, you have your magnify. Let's start from your eyepiece down to your light source. Okay, and so your eyepiece here, accordingly, this one is where you will what you call this. You will observe. Okay, and so you observe the specimen, and with this, what will this do? This one is where you will observe again, and this one will remagnify the image that is formed by the objective. With that being said, it is a what you call this a secondary lens. Okay, and so a secondary lens that will further magnify the image that is captured by your objective lenses. Okay, and so with this, it is a system of lenses located closest to the viewer's eye. Okay, and so for your eyepiece, and then you have your in your eyepiece, you also have your diopter adjustment. That the use of this one is to compensate for the difference in the observer's sight or vision between the left and the right eye. Okay, and so that is why accordingly you can remove your glasses to view a an object under the microscope. This one can be adjusted. Okay, and yes, an illustration of your compound microscope. In this one, okay, and so in this area, you can, yes, this is your eyepiece, and this part, you can actually rotate this one. This is your diopter adjustment. Okay, your arm. Your arm with this, of course, it will connect your parts of your microscope. Okay, and so your arm, it is utilized to hold the microscope. And your revolving, it houses also your revolving nose piece. Your revolving nose piece here, these are rotating parts that easily changes the magnification of the objective. And yes, it holds the objectives. Okay. And so this part of this one is your revolving nose piece. Okay? And your objective lenses. This objective lenses, they are your primary lens that magnifies the image. They provide the primary image. Okay? And with this, accordingly, that is the most important part that will give you a clear image of the specimen. Okay, and so with this accordingly, you have the higher the magnification number of an objective, the greater is the feature or detail accordingly. And yes, you have your course adjustment knob. Your course adjustment knob is utilized to to obtain a coarse focus by moving the stage up and down. Okay, and so this one is usually utilized when using your low power objective together with your scanning objective. Okay, and so to give you a coarse focus. And then you have your fine adjustment knob. Your fine adjustment knob will give you a fine focus by moving the stage up and down and gradually. Of course, after your coarse adjustment, you need to do a fine focus. This one is usually utilized when using your high power objective and also with your oil immersion one. And then you have your mechanical stage. That is where the sample accordingly is placed. That is where your glass slide is placed. Okay. And so with this, you have here for your eyepiece, your body tube, your draw tube, you have the arm, you have your revolving nose piece or your turret, you have your objective lenses, You have your stage, you have your course adjustment knob. Let's call it as course adjustment knob, and then fine adjustment knob. Okay, and so that is why when you were asked about the knob, then you answer it with a knob also. Okay, your condenser, and then the rest of the parts of the microscope. This is for your mechanical stage. Yes, it can be moved. Mechanical stage. Okay, and then you have here your condenser that will focus the light on the specimen. It will give evenly distribute accordingly and optimally focus light from the illumination source onto the specimen. And your iris diaphragm, this one will control or regulate the diameter of light beam that strikes the sample. Okay, and so it is a diaphragm. And with this, it reduces stray light accordingly. Okay, and so your condenser and iris diaphragm, they are located below the mechanical stage. Okay, and then you have your base. Your base here, accordingly, it will support the entire microscope, of course. And then you have your rheostat or the light source. This is a knob that controls, sorry, rheostat or your light control knob. This one will control the light intensity and your mechanical stage adjustment knobs, or some references call it as your X and Y adjustment knob of your microscope. With this, they control the stage movement. For this one, you have your what they call this the top knob, and then the smaller knob that is located at the bottom. Okay, and so for the top knob, this one is utilized for forward and back movement. Okay, and then the other one is utilized for left and right movement. Okay, that is for your mechanical stage. I sorry, mechanical stage adjustment knobs. And then you have your light source. Your light source usually for a bright field or for your compound microscope, or usually for light microscope, the light source, they are located below the specimen. Okay, and so usually for your light source, they are made of tungsten or tungsten halogen lamp. Okay, and so tungsten or tungsten halogen lamp. And the light source, this one is regulated by your rheostat or your light intensity knob. Okay, let's take a look at your terminologies utilized in handling the microscope. Okay, and so when we say magnification, that is the process of enlarging or magnifying an object without affecting its actual size. And yes, we can magnify an object using a simple magnifying glass. Okay, also, okay, and so but then we will not be using magnifying glass to magnify our object. We will be utilizing microscope to do the magnification. Okay, and so when you say total magnification, that is the okay, when we say total magnification, that is obtained by multiplying your ocular lens or the magnification of the ocular lens multiplied it by your objective magnification. Okay, and so please note that in your ocular lens, the conventional ocular lens, they have a 10 times magnification, or at least 10 or 11 times magnification. And then of course for your objectives, they have 10, 40, and 100 times magnification. Okay, and so with this, of course, you need to multiply 10 times 10 to get your total magnification if you are using an objective with a yellow band. Okay, let's take a look at your objectives. For your objectives, again, they are either the magnification of your eyepiece, they have 10 or 11 times. Okay. Your scanner, they have 4 times magnification. And then your low power objective, the ones with yellow band, they have 10 times magnification, your high power objective. The ones with the blue band, they have a 40 times magnification. And then oil immersion objective, the ones with a white band, they have 100 times magnification. Okay, and so given the formula earlier that the magnification is obtained by multiplying your individual magnification, multiplying it with the eyepiece, which is usually 10 times magnification, then you will obtain such. Okay, and so when you are using scanner, your scanning objective, 4 times 10 will give you 40. When you are using low power objective to view a I mean an object under the microscope, you multiply it by 10, 10 times 10 to give you 100. And of course, you do the rest for this one. Of course, that is for us. Okay. Next, you have your focal point. Your focal point, that is your specific point at which parallel rays of light converge after passing through a lens accordingly. And then your focal length, that is the distance from the lens center to a point where the parallel rays are focused on the optical axis. Okay, and so you have another definition for this. Okay, parfocal. When you say parfocal, that is the ability of an object, I mean, ability of the objectives to remain in focus regardless of the object that is being used. Okay, and so let's say, for example, you shift that you are using the blue yellow band, you're using the yellow band to view an object and you got the crisp detail. Okay, and so after that you're going to shift to a higher magnification, let's say high power objective. Okay, and so it is said to be parfocal when you shift it to high power objective and you still got a crisp detail of your sample. Okay, and so it still remains in focus. And then power-centered, the ability of objective lenses to retain the same central field of view when user switches from one objective to another. Okay, and so the field of view for this one. Okay, and so it maintains the same central field of view. That is for power-centered. Okay, moving on to your resolution or resolving power, that is the ability of a lens to distinguish between 2 points or objects as separate accordingly. This one accordingly describes the ability of the lens system to reveal fine detail. Okay, and so for this one, in what you call this, in manipulating the microscope, it is somewhat similar with manipulating a camera. Okay, and so for this one, and then your working distance, that is the distance between the objective and the cover slip on the slide. The distance between the tip of your objective lens and the cover slip of your slide. Okay, and so for this one. And yes, accordingly, your working distance decreases as the magnification of the objective increases accordingly. And finally, your numerical aperture, the number that indicates the resolving power of a lens system. Okay, that is for your numerical aperture. And then yes, let's move on to your types of microscope. Please, it should be microscopy. Okay, and so let's take a look at the techniques. Okay, and so that are utilized in microscopy. Again, when I say microscopy, that is the technique, and then when I say microscope, that is the device. Okay, and so with this one, your bright field microscope, it consists of two lens system. You have your objective that are actually closest to the specimen, and then the eyepiece that will further magnify. As what we said earlier, your objective lenses, they will provide the primary magnification, and for your eyepiece, they will further, I will give you the final magnification of your sample, give you the final image. Okay, and so the image in your bright field microscope, they will have a in your bright field microscope, the sample appears dark against a bright background. Okay, and so you have a bright field for this one. Okay, your bright field microscope still. Okay, and so that is the image presented. And then you have your phase contrast. It permits detailed viewing of low refractile components and of living cells. Okay, and yes, this one is used to view unstained cells. As what I've said last time, that for us to get a better understanding of a better view of your cellular tissue components, we need to give it contrast. And how are we going to give contrast? We do stain. We stain the sample. Okay, and so but then in phase contrast, this one can what you call this can permit it permits detailed viewing of low refractile components and of your living cells. Again, this one is used for unstained samples. Okay, and please note that bright field microscope can be converted into a phase contrast microscope by what they call this using of annular rings in the condenser and objective lens. Okay, in your phase contrast, you have areas of specimen that appear light and dark with halos of various intensities. Okay, those are images obtained using a phase contrast microscope. Moving on, you have your dark field microscope. This one is used to identify live Treponema pallidum, Leptospira, and the Vibrio cholerae accordingly. Okay, and so your object in your dark field microscope will appear against a dark background. Your object will appear bright against a dark background. Okay, that is for your dark field. This one is an illustration of a sample obtained using a dark field microscopy. Okay, and so this one is a Vibrio. Yes, this one is a Vibrio cholerae bacteria. Okay, let's take a look at your polarizing microscope. This one is used to observe the birefringent properties of a specimen. Okay, and so with this, of course, when you utilize polarizing, then you will have a positive and negative birefringent results. And yes, this one is used in identification of crystals in urine and synovial fluid and confirmation of oval fat bodies in the urine sediment. Okay, and so with this, we will not be utilizing such in histology. And yes, you have your electron microscopy. You have two types of, sorry, electron microscope. You have two types. You have your transmission and scanning electron microscope. Okay, and so with this, they do not utilize a light source. They do not utilize tungsten or tungsten halogen as a light source, but then they utilize beam of electrons. Okay, and so they utilize beam of electrons to provide us a view or an image. Okay, and so with this, your transmission, your electrons pass directly through the specimen, and your scanning, your electron strikes the surface of the specimen. That is why in your scanning, it will provide you a three-dimensional shape of the specimen. Okay, and so for this one, in your transmission, okay, and so it only give you a two-dimensional view of your sample. Okay, and so in terms of magnification, your transmission electron microscope will give you a greater than 100,000 times magnification. While you're scanning, it will only give you greater than 1,000 times magnification. Okay? And yes, for your fluorescence. It will allow visualization of naturally fluorescent microorganisms or those stained by fluorescent dyes. Okay, and so you have your two filters actually used for this one. You have your excitation and your barrier filter. And yes, it uses fluorophores. Okay, and so it uses fluorophores somewhat to stain your sample. Okay, and so in the image, the specimen will appear green, yellow, or orange against a black background based on the fluorophore, based on the fluorophore that is used. Okay, your immersion oil, this one is utilized when you are uh utilizing your oil immersion objective. And what does it do? It will enhance the resolution of the microscope and is used to fill the spaces between the objective lens and the glass slide accordingly. And aside from that, it prevents light rays from dispersing and charging their wavelength after passing through the sample. And yes, the immersion oil, the oil that is usually utilized, you have it as your cedarwood oil. And please note of the care of your microscope. You should carry the microscope with two hands and always hold the microscope in vertical position and clean the optical surfaces with a good quality lens tissue and commercial lens cleanser. Okay, and so after utilizing your oil immersion objective, please wipe the lens using a clean tissue paper or clean lens paper. And again, clean the oil immersion lens after use. And finally, okay, and so you have your do's and don'ts accordingly. You do use lens paper on optical surfaces. You always use commercial lens paper to clean the optical surfaces. You protect the microscope from dust. That is why it should be covered when not unused. Okay, and yes, document cleaning and maintenance and have your microscope professionally serviced annually. Do not do this. Never use gauze, facial tissue, or lint-free tissue on lens surfaces. Never touch the optical surfaces. Never wipe off a dust or, or particulate matter. Remove using suitable brush or syringe. And then never wear mascara in performing microscopy because it will uh, obliterate or it will somewhat attach to the lens of your eyepiece. Okay, never clean the back lens of the objectives, never use grease or oil on mechanical parts, never disassemble, and never leave microscope tubes without eyepieces accordingly. Okay, that is for such. Okay, and so for your parts of the microscope, again, this is your ocular lens. This one is for a binocular compound microscope. Your diopter adjustment, you have this one. Your diopter adjustment, again, this one can be adjusted to compensate for the differences in vision. Your revolving nose piece, your objective lenses, you have your head somewhat, you have your draw tube, you have your arm, you have your mechanical stage, your stage clip, your aperture, your diaphragm, your condenser, your light source, your base, of course. You have your stage control knob. You have your X and Y control knobs. And then your fine adjustment and your coarse adjustment knob. This one will be the coarse adjustment knob and the fine adjustment knob. Okay. And that's it for your microscope.